Hey, in this video, we're going to look at functions of multiple variables. We're going to look at inputs and outputs. And similarly, we're going to look at domain and range of these multivariable functions. We'll look at an application and sort of visualize some of these things in a program called GeoGebra as well. So let's get started with defining. Let's start with a function in two variables. So a function, let's call it f in two variables. A function f in two variables takes an ordered pair input, let's call it x comma y, out of R2. So x and y are both real numbers here. So we're taking an ordered pair input x comma y from R2 and assigns an output, let's call it z, which is also a real number, assigns an output z, okay? The graph of this function f is a surface in R3, so in three-dimensional space. So we'll kind of get a handle on why these things happen here. Get my notation right. So we take an ordered pair input, two real numbers, and assign to that an output that is a real number as well. We've seen this sort of thing before. A plane is a surface in R3. A plane is a surface in R3. Okay. When written as a function, it will be something like z equals some linear function in x and y. Okay, so you might solve for z, and then the expression you get on the other side would be a linear function using the variables x and y. So it's a surface. A plane is a surface in R3. You can write it maybe as a function as well. Let's look at some illustrations of this idea that z equals a function of x comma y. Okay. First of all, the notation for functions in multiple variables, the input is an ordered pair. So you might think of it as f of the ordered pair x comma y, but we tend to leave off the second set of parentheses in this process due to the simple redundancy of them. So understand that the input is an ordered pair. We just often don't enclose the ordered pair in a second set of parentheses in function notation. Okay, so let me grab my pen and we can kind of look at how to visualize a function in two variables. So one way to do it is to pick an input from R2. So this is R2 here, and our inputs are ordered pairs x and y. So this will be the typical xy Cartesian plane. And you could take an ordered pair from this xy plane, say this ordered pair right here, x comma y, and you could map it to an output that is a real number as well. So we could list our outputs over here. These could be our z values, and it could map to some particular z right here. So you could visualize an ordered pair input mapping to a real number, R1, if you will, on the right-hand side. Okay, so that's one way to visualize it, map an ordered pair to a real number. Another way to visualize it is in R3. So in R3, you just map it all out together. So let me see what we've got here. So here's our positive x-axis. Here's our positive y-axis. Here's our positive z-axis. you could pick an ordered pair xy in the xy plane. So let's say in the xy plane, I'm going to pick this x value, somewhere along this x value, and then maybe I'll pick this y value, okay? And so I've generated an ordered pair right here in the xy plane, okay? And to that point in the xy plane, I could assign an output a z value. And so to get the z value, I would simply, maybe it's a positive z value, so I'd go up from that point vertically, and I would land at some point in R3, and this would be a point on the surface of our function, a point on the surface of our function f, and that point would be the ordered triple x comma y comma z. So the x and y are the x and y coordinates, and the z coordinate would be the output z. All right. So that's one way to visualize it. The inputs are in the xy plane, and the outputs are points in 3 space that when you plot all of the points, you would get some sort of surface in 3 dimensions. Okay, so that's a couple ways to visualize functions in 2 variables. Let's look at an example. Let the function f of x comma y equal the fraction where the numerator is 5x plus 3y and the denominator, let's say, is x plus y. Okay. And the first thing we might do with this is, well, first of all, let's just look at what this function looks like in 3 space. If we were to graph it, what surface would this look like? So I've got it prepared here in GeoGebra. So this is R3 in GeoGebra, and if I turn on this function, you can see what it looks like here. I can kind of spin it around, and you can imagine it's pretty interesting. Interesting surface there in 3 dimensions. You can see it's got some kind of gap there in the middle. That's kind of interesting as well. You can visualize it from above, and so on and so forth. So this is the graph of this curve, 5x plus 3y over x plus y, just to get a visualization. But let's do something with it. Let's determine, let's say, f of the input, the ordered pair, -2, 3. Okay, and furthermore, let's discuss the graphical meaning of this point, or of this. Oh, I gave it away. Shoot. Discuss the graphical meaning of this. So, all right. So this means that x is -2 and y is 3. So f of -2, 3 simply equals 5 times -2 plus 3 times 3 over -2 plus 3. And so if we look at that point, we get -10 plus 9, that's -1 over -2 plus 3 is 1. And we can see that we get an output of -1. So what this is saying is when x is -2 and y is 3, it outputs -1. If we go back to our graph here, and we look at the order triple where x is -2, y is 3, and z is -1. Let me see, was that the point we had? I forgot already. Yes, all right. If we look at that, and then we kind of look around at our point here, we can see that point, can zoom in maybe even, that point is on the surface, okay? So graphically what that means is, if you look at the ordered pair -2, 3 in the xy plane, which is back here, then its z value is -1 down here at that point on the curve, okay? So the point -2, 3, 1 is on the surface f, because this function is a surface, so that point is on that surface, okay? Example 2 dealing with this, let's determine Let's determine something like f of x comma y plus h. That might look familiar when you're dealing with like the limit definition of a derivative in one dimension. You might look at f of x plus h or something. So you can do similar things here with functions of multiple variables. So we're going to plug in x for x and y plus h for y. So we get f of x comma y plus h equals, I'm working horizontally so we can see it up here, equals 5x plus 3 times the quantity y plus h over x plus the quantity y plus h. And we can just simplify that if we wanted to by distributing the 3 to get 5x plus 3y plus 3h. And on bottom, we could have x plus y plus h. And you could do things like let h go to 0. You could apply a limit there maybe or something like that. But that's evaluating this function at non-numerical inputs. Let's determine, number 3, let's determine f of, this will be an interesting example, f of x comma x. All right. So we're going to plug x in for x and x in for y. So f of x comma x equals 5x plus 3x over x plus x. And this simplifies a little bit. We get 8x over 2x, which simplifies down to 4. So let me show you what's going on here. Notice that y is equal to x, okay? Y is equal to x. Let's go back to our GeoGebra animation. Let me plot the line y equals x. Let me turn this point off. Let me turn off the curve for a second. Let me plot the curve where y equals x. So that might be t comma t, and then we'll keep z at 0 because we're in the xy plane. So x and y are both given by the, in fact, let's just use x. Maybe that'll work. X for x and y, and then z is 0. And then our parameters x, and we'll let x run from maybe -10 to 10. So this is the line y equals x right here, okay, on the xy plane. Let's turn our curve back on and understand what happens whenever we look back at our notes here. If we input all of the ordered pairs on that line, x comma x, it says the output is 4. We get a constant output. Well, look at the GeoGebra diagram here. I've already got it sketched out. If I look at the outputs of all the points on this line, notice how they are all 4. And all of those points are on the surface that we see here. So if x and y are equal to each other, like if I plug in 2 for x and 2 for y, my output's going to be 4. And that's true everywhere along this line where x and y are equal in the xy plane. They all output 4, and you can see it on the surface that we see here. Okay, so kind of interesting there. Let's see here. Do I have another example? Yeah. Okay, so let's introduce this idea of domain. Find the domain of, and let's go back and copy the function so we can see it all. Find the domain of this guy. When you're working with a function of one variable, so you've got 2 dimensions when you're dealing with a function of one variable, the domain is just, the x values that you can plug in. But now when we're talking about domain, we need valid ordered pair inputs. Valid ordered pair inputs. So it's a little trickier now. So in this case, what do I mean by valid? I mean ordered pair x and y inputs that won't cause issues with calculating the output. So in this case, we can see that we're dividing by x plus y. So in this problem, we do not want x plus y to equal 0. Okay, so the domain of this function is all ordered pairs x comma y such that, by the way, this is called set builder notation. So a brace to indicate a set. It's a set of all ordered pairs x comma y, and then the vertical bar means such that x plus y does not equal 0. Okay. Well, that's also equivalent to the set, or equal to the set, we could say, x comma y such that x does not equal negative y. So we could, this is the domain. Neither one of these is an appropriate way to write the domain of this function, but let's understand what that means. If we look at a graph of where x equals negative y, let's restrict our domain to the xy plane. So our domain now consists of ordered pairs from R2, so we have to look at R2 for domain. X equals negative y is anywhere along this line. This is the line x equals negative y. We do not want any point on this line to be in our domain. So our domain is any ordered pair. Our domain is any ordered pair on this side of the line or on this side of the line. It's every ordered pair except for the ones that are on that line. So we can visualize that graphically. Okay, so hopefully that helps with what domain is when you're dealing with a function of more than one variable. It's valid, in this case, ordered pair inputs. Okay, so let's review what types of things you might run into issues with on domain. Let's recall some domain restrictions. Okay, we just saw we can't divide by 0. We also cannot take an even root, like a square root or a fourth root of a negative number, because we'll get imaginary numbers which are not real numbers. We're working with real number inputs and outputs here. And then another one that we might run into is we can only take logs of positive numbers. So you can only have positive logs. So if we're dividing, we can't divide by 0. We can't divide by 0. We can't take a fourth root of a negative or any even root. I don't know why I focused on fourth root. We can't take an even root of a negative. And we can only have logs of positives. Okay? So keep that in mind here as we work through some more examples. So let's practice with domain and range. You know what? Before we practice, let's remind ourselves of a couple other things. An even root. Let's talk about the outputs now. An even root outputs 0 or greater. Outputs a number greater than or equal to 0. It cannot output a negative number. Okay. Any kind of log will can output any number from negative infinity to positive infinity. Okay, just some things to think about here as we move forward. So, because we're going to be working on domain and range moving forward. So let's try some of these. Determine the domain and range of each. In number 1, let's look at f of x comma y equals the square root of 3x plus 2 plus the square root of y minus 4. All right, we want the domain and the range. So let's talk domain first. The domain is the set of all ordered pairs such that, now we've got two even roots, we've got two square roots. We have to satisfy both conditions for those. We know that 3x plus 2 has to be, it can't be negative. That means it has to be greater than or equal to 0. And y minus 4 also has to be greater than or equal to 0. Okay? And that's a perfectly acceptable answer for the domain of this function. But let's analyze it a little bit further. This means that x has to be greater than or equal to negative 2/3, and this means that y has to be greater than or equal to 4. If we look at the domain again in R2, let's say this is negative 2/3 on the x-axis and this is 4 on the y-axis. So x has to be greater than or equal to negative 2/3. So it has to be any x value to the right. But y has to also be greater than or equal to 4. So that's x values up here. So our domain here happens to be all of the points on these two lines or to the right and above those two lines. Every ordered pair in this shaded region is a valid input to this function. Okay? So this is our domain, all of those points. Let's talk about the range. We know a square root can output 0 or higher. So this function here, we know that we could plug in an x value and make it equal to 0. And we know over here we could plug in 4 for y and make this guy equal to 0. So we know our range is going to start at 0. We could say z is greater than or equal to 0. And then the question is there any bound on how big the output could get? Well, if say we just fix y to be 4. Say we just pick a 4 for y. So this guy's going to 0. Well, you can pick x values infinitely large so that this guy is going to go to infinity. Therefore, our range starts at 0. Well, it can output 0 and it can output every number bigger than that. So our range is just all z values greater than or equal to 0. If you want to write that in set builder notation, you could say the set of all z's such that z is greater than or equal to 0. Interval notation, of course, would be bracket 0, comma, infinity. We can't use interval notation for the domain because the domain deals with ordered pairs, not individual numbers. All right, so that's domain and range. Let's do another one with the same instructions. Let's say our function is h of x comma y equals the square root of 16 minus x squared minus y squared. Okay. And we want the domain and the range. Well, let's start with domain again. Okay, so for our domain, we've got a square root. So our domain is going to be the set of all ordered pairs x and xy, such that what's under the square root, 16 minus x squared minus y squared, is greater than or equal to 0. Well, you might recognize this. This has something to do with a circle. So this is an okay answer for domain, but we can understand it even better. We know that in this case, let's say I add my x squared and y squared over. I know that 16 is greater than or equal to x squared plus y squared. So if we look at that in the xy plane, x squared plus y squared equals 16 is a circle centered at the origin with radius 4. Okay, so 4 is our radius. And x squared plus y squared is less than or equal to 16. So that would be every point within this circle or on the circle. So our domain is every point within or on this circle in the xy plane. Okay, it's kind of interesting. We cannot input points outside of here. For example, if you try the point 5, 0, if you plug in 5 for x, that's 25, and 0 for y, you're taking 16 minus 25, which is negative 9, minus 0, which is still negative 9. So we have the square root of negative 9. We don't get a real number output. So you can see why points outside of this circle would result in a negative under the square root. Now let's talk range. This one's a little bit trickier. We know that a square root will output something greater than or equal to 0. And we also know, so let's first see if we can figure out some way to output 0. Okay, so we could plug in 4 for x to make that 16 and 0 for y. So we'd have 16 minus 0. So we can output 0. So we know we're going to output 0, okay? So that's on the low end. We can output 0. Having trouble spelling output. But we can output 0. Now, what's the biggest number we can output? Well, what we're doing here is we're taking 16 minus 2 positive numbers. So the biggest that this output could ever be is if both of these positive numbers, not positive, but they can't be negative numbers, if both of these are 0. So if I plug in 0 for x and 0 for y, I'm going to get the square root of 16. If I plug in anything bigger than 0 for either of these, I'm going to be taking 16 minus something, and I'm going to get something smaller than the square root of 16. So I know I can output 0 all the way to the square root of 16. So our range is 0 to 4, including both of them, because I can output 0 and I can output 4. That's an interval notation, or I could say the set of all z such that z is greater than or equal to 0 and less than or equal to 4. Okay. Let's take a look at the graph of this function just to see what's going on here. Let me turn this guy off. So we have h of x comma y equals the square root of 16 minus x squared minus y squared. And here's our graph. You can see it's half of a sphere. And our domain, our domain is in the xy plane. If I look down at the xy plane, you can see it's our circle centered at the origin of radius 4. That's our domain. Our range is the z values. You can see there the z values run from 0 up to 4, just as we anticipated. Okay. All right, let's do another example. Let's say we're looking at the function g of x comma y equals the natural log of the expression, the quantity x minus 2 squared plus the quantity y plus 5 squared minus 6, and we'll close our brackets there. And again, we want the domain and the range. So let's start with domain. It's the set of all ordered pairs, because our inputs are ordered pairs, such that, well, a natural log, the argument has to be positive. So in this case, we need x minus 2 squared plus y plus 5 squared minus 6. We need that to be greater than 0. Okay? Or, making it a little bit easier to recognize, we could just add the 6 over. X minus 2 squared plus y plus 5 squared is greater than 6. And that again is a circle. So in this case, if we visualize what's going on, centered at 2, -5, so let's say 2, -5, that's our center, and the radius is the square root of 6, so that's like 2 point something. So let's say it's like right here. So our circle looks like this. Okay, and we want all of the points that have a value greater than 6. So those are going to be the points outside of this circle, which goes on forever in every direction. So our domain is all of the ordered pairs that live outside of this circle. And because it's greater than 6, not greater than or equal to, in fact, we don't even want to include the points on the perimeter of this circle, okay? So we might indicate that with a dashed line. So we can only pick points outside of the circle. You can see if you choose a point inside, like 2, -5, you're going to get 2 minus 2 is 0, -5 plus 5, 0. You get 0 is greater than 6. That's not true. If you plug in 0, you're going to get a negative number inside your natural log. Okay, so we can't have any point inside the circle. Now let's talk about the range of this function. A natural log will typically output -infinity to infinity. So if you look at this, the graph of the natural log function in 2 dimensions, it looks like this. So if it's going to go to -infinity, you need to be able to input values that get infinitely close to 0. Okay, and because we can plug in numbers to make the x portion of this 0 and the y portion of this, not 0, but if we want to plug in numbers for the stuff circled here to get 6, 6 minus 6 is 0. And we could do that. Let's see here. The easiest way to think of this is keep one of your variables constant. So maybe let x be 2. So that's like this isn't here now. So could we plug in a number here to make the rest of this go to 0? And the answer is yes, because we have a positive number minus 6. So we could easily plug in a number for y to make this equal to 6. It's going to involve a square root, but we could easily turn the inside of the argument of the logarithm into something infinitely close to 0. We could even turn it into 0. So that's going to tell us that our range is going to go to negative infinity. Okay, so we know our range is going to go from negative infinity. Now, the question is, how does it go to positive infinity? Well, the natural log goes to positive infinity as the x values increase without bound, or the inputs increase. We can plug in big enough values for x and y to make the argument of this logarithm as big as we want. So, in fact, this function can output everything up to positive infinity as well. Okay, so the range here, you could write as negative infinity to infinity. You could just write it as all real numbers. Okay, now let's take a look at the graph of this one as well. Let's see here. Let's turn this off. We've got g of x comma y equals the natural log of, I think it was, let me make sure here, x minus 2 squared plus y plus 5 squared minus 6. I think that's what it was. Yeah. Okay, so you can, I'll zoom out here so you can see it a little bit. You get this really interesting curve that sort of has this infinitely deep hole here in the middle. And so you can see our domain, as we found, is all of the points outside of this circle in the xy plane. And you can also see the z values, maybe the z values go to negative infinity, and you can't really tell because it's a log function, so it grows, but it's really slow, but it will go to positive infinity eventually. Okay, what else do we have on the agenda here? Okay, so that is an introduction to functions of two variables. You can apply the same ideas to get a function, let's say f of n variables. A function f of n variables takes an ordered, not an ordered pair, but an ordered n tuple input. So what we can call that like x sub 1, x sub 2, dot, 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 all the way to x sub n. It takes n numbers in order as an input, an ordered n tuple input, and outputs, let's move this down, and outputs, again, some real number, let's say y here. Oh, furthermore, sorry, our ordered n tuple comes from r to the n. So all of those coordinates are real number coordinates still. And y is also a real number. Okay, so you could say z if you like. If you don't want to think of it outputting z, that's fine. But it takes an ordered n tuple, all from real numbers, and outputs a real number as well. So no big deal there, simple enough to understand. Let's do a quick example with this guy. Let's f of, we'll look at a function of three variables. So f of x, y, z. I could have used x1, x2, x3, it doesn't matter. But typically a function of three variables, you think as the inputs x, y, and z, the order triple. So f of x, y, z equals the natural log of something similar. So let's look at 16 minus x squared minus y squared minus z squared now. Okay, and question one, let's determine f of 0, 0, 0. Determine f of 0, 0, 0. Well, that's no problem. That means plug in 0 for x, 0 for y, and 0 for z. So we get the natural log of 16 minus 0 minus 0 minus 0. So our output is just the natural log of 16. So now we're taking this ordered triple, 0, 0, 0, and outputting another number that we might think of as like a w or something, since x, y, and z are taken. Okay. Now here's an interesting question. Let's determine the domain of this function f. The domain. It's similar to before, except now valid inputs are ordered triples. Okay, valid inputs are ordered triples. So with the natural log, we have to make sure the argument's positive. So the domain of this is going to be all ordered triples x, y, z, such that the argument 16 minus x squared minus y squared minus z squared is greater than 0. Okay. And as we saw before, we could rewrite that as the ordered triples x, y, z, such that if we add the x squared, the y squared, and the z squared over, we get x squared plus y squared plus z squared is less than 16. And what does that mean geometrically? So what that's telling us geometrically is x squared plus y squared plus z squared in 3 dimensions. In 3 dimensions now. So our domain comes from R3 instead of R2 like before. It's a sphere of radius 4. It's kind of hard to draw, so I'll just kind of fake it here. Okay, it's a sphere of radius 4 in 3 dimensions, and we want all the points within. We want all the points within that sphere will be valid inputs to this function. Now the hard part about this is if you want to graph it, you'd have to graph it in 4 dimensions because you'd have your 3 inputs from R3 and you'd have to plot it to a point that is your output. So that's difficult. So instead, this is better to think of, all right, here's R3 and our domain is all the points inside the sphere. And if you pick a point inside the sphere, it's going to map to its output over here, whatever that may be, that is a real number. Okay. So the domain are all the points over here, and the points that you could get out of these outputs would be your range in just R because you output a real number. So there's no way to actually graph this in 4 dimensions like we were doing with a function of 2 variables in 3 dimensions. Okay. All right. So that's functions of 2 variables, functions of n variables. You could do domain and all those sorts of things here. You could do range even. But let's move on to an application. Functions of multiple variables. You can imagine most of the time in the real world when you're using a physics formula or a biology formula or something, there's several factors to calculate things, and those often will be functions of multiple variables. So let's look at an example here where we have something like the volume of an oxygen tank, let's say in cubic inches, depends on, it has a particular shape. We won't get into that, but let's say the volume of an oxygen tank depends on its radius r and its height, let's say h. Okay, both measured in inches. So since the volume depends on the radius and the height, we can write that v equals some function of r and h, f of r comma h. And we're going to look at a table that shows us the relationship here. So the table below gives values of v, meaning volume, for various radii and heights. Okay, so I'm going to pause the video for a second. I'm going to go grab the table, and then if you want to copy it, if you're taking notes, you can pause the video and copy it into your notes as well. Okay, so we have our table here. We've got our R values listed across the top. Those are measured in inches. We've got our height values measured across the left, measured in inches. And the numbers here are the corresponding volumes. Okay, so let's answer a question here about this function of 2 variables. What is the value of, let's say, f of 2 comma 18, and what does it mean? What is the value of f of 2 comma 18, and what does it mean? So we know that f takes r as its first coordinate input and h as its second coordinate of the ordered pair input. So we know that 2 is our radius and that 18 is our height. And so if we cross-reference the radius of 2 with the height of 18, we get this 260, which is the volume, okay? So let's discuss what that means and talk about the proper notation. So f of 2 comma 18 equals outputs 260. That's the first part of the question. And what does it mean? Well, it means when a tank has a radius of 2 inches and a height of 18 inches, its volume is 260 cubic inches. So pretty simple. Again, in real world applications, we often get multiple variable problems, okay? And so these don't have to have a graphical meaning. As a mathematician, we like to make connections in lots of different ways, maybe via a graph, but they don't have to have a graphical meaning necessarily. Question B, and this will be the end of the video, for what value of, let's see here, for what value of h is f of 3 comma h equal to 339? And what does this mean? What does this mean? Okay. For what value of h is f of 3 comma h equal to 339? So now we are looking for a radius of 3 and a volume of 339. So in our radius of 3 column, or sorry, yeah, radius of 3 column, we're looking for a volume of 339. And the question is, for what value of h is that the volume? And the answer is 8. Okay, so we know that h equals 8. So that's the answer to the first part of the question, for what value of h is this true? And the second part of the question is, what does that mean? So what does that mean here? It means if we have a radius of 3 inches and a volume of 339 cubic inches, the height of the tank must be 8 inches. Okay? Pretty simple stuff. Just want to show you a real-world application, perhaps, of how functions and multivariables could be used. This one's simple. It's a function of 2 variables. But we didn't have an equation. We just had a table of values. If you had an equation, you could plug them in and actually do some algebra to solve. But hopefully you have a better understanding of functions of multiple variables now. You're equipped to maybe go do some calculus with them.